we have been discussing about this microsystems for micro robots. So, in today's lectures, we will be discussing about the micro manipulation for microsystem robot. In fact, we have been discussing about this AFM. So, in today's lecture, we will discuss about the different modes of AFM, like how an AFM is used as a kind of a micro and a nano robot as far as characterization perspective point of view. So, as far as the modes of AFMs are concerned, so one mode is called as a contact mode. So, as far as in this contact mode is like it has a tip, and then this tip will never leave the surface used for a very high resolution imaging. So, the maximum vertical force is also controlled to minimize the compression of the sample, and it has a fast scanning and it is highly used for a kind of a good surface roughness. So, ideally what will happen is this particular tip will try to move along the surface, and it will try to trace the profile, and from the profile we can observe a kind of a roughness pattern which comes out of it. So, and second thing is these can damage. So, ideally such kind of contact mode systems are concerned. So, these contact mode systems has a possibility to damage the surface. So, like for example, if you have some kind of porous soft structures or porous oxidic structures, there is a chance that it may damage the surface if the measurement is done in the air atmosphere. And then like as far as these lateral forces are concerned, so these lateral forces can also distort the image, for which will have a kind of an impact on the system. So, ideally these contact modes are effectively used for a kind of a coating or a kind of a thin film which gets exhibited. Now, let us discuss about the second mode, which is called as a tapping mode. As far as this tapping mode is concerned, so in this tapping mode the tip will not be in touch with the system. So, ideally what will happen is the tip will be, it will not in contact with the surface, there will be a gap between the surface and the tip, and it is almost we can have a kind of an oscillating cycle as shown over here. So, as far as in this particular case is concerned, so there is a kind of a charge transfer which happens between the tip and the surface. So, appropriately we can study the overall orientation of this charge transfer. So, it is used for imaging the samples which are not firmly stuck on the surface, such as molecules, and the cantilever is driven close to the resonance of the system to give an amplitude for oscillation, and the cantilever oscillates and tips makes a repulsive contact with the surface at the lowest point of the oscillation. So, ideally like when we try to observe the tip, so at the lowest point of oscillation we will be having a repulsive force, and at the top edge we will be having a attractive force. So, there will be a kind of like deviation between, or there will be a kind of repercussion between the attraction between the peak and the valley. So, peak we will be having a kind of an attraction, and in the valley there will be a kind of a repulsion. So, based on that we can generate a kind of a profile, and these profiles will give a kind of an indication about the traces, about the overall surface features which are being deployed. Okay. So, these like oscillation can be achieved with a small piezo element in the cantilever holder, which we had discussed a lot in the last class also, and it has a kind of an AC magnetic field and a piezoelectric cantilevers or a periodic heating with the laser beam. So, one of the important key aspect of this particular mode is like it has an imaging force which are bit lower. Now, let us discuss about the next mode, which is called as force modulation mode. So, as far as these force modulation mode is concerned, in this mode the tip does not leave the surface, but it makes a small oscillation. So, this is a kind of a dynamic form of contact mode called a kind of a force modulation mode. So, the cantilever is kept oscillating with a fixed amplitude, and its resonance frequency is being monitored, and image is formed by a kind of a constant frequency shift. The difference between the current frequency and the free resonant frequency are being deployed. So, ideally this is a kind of a force spectroscopy mode which are being deployed. So, wherever kind of a corrugated structures are there, such kind of force operated AFM modes, that is force modulated AFM modes can be efficiently deployed. Now, let us talk about the non-contact mode based system. So, as far as in this non-contact mode based system, like the cantilever in this non-contact mode based system, it is almost equivalent to a kind of a tapping mode, whereas in the case of a non-contact mode based system, the cantilever oscillates close to the sample surface at a resonance frequency, but never makes a kind of a contact. So, there is a kind of a force which is exerted. So, there will be a kind of an attractive force and a capillary force in air creates a possibility of the tip in touching the surface. It requires a very stiff cantilevers to overcome the attractive forces and operate without touching the surfaces. A long range of forces between the tip and the surfaces decreases the resonant frequency of the cantilever, and this decreases in resonant frequency combined with the feedback loop system, which maintains a kind of a constant oscillation amplitude or frequency by adjusting the tip to a sample distance. This tip to a sample distance data at each point is used by a software to construct a kind of a topological image. So, ideally this topological image will have the complete information about the peaks and the valleys. From the peaks and the valleys, we can estimate the overall undulation which comes out of it. Now, with reference to all these modes, it is observed that this feedback plays a vital role. So, when we try to observe this feedback system, like with reference to AFM perspective point of view, it is bit critical. Like in fact, in the earlier classes also we have seen like these feedbacks sorry, are taken from both the piezo layers as well as the piezo scanners. So, within the piezo layers and the piezo scanners, so the feedback loop is being embedded and appropriately the signals are taken care. So, let us discuss about the strategies which are followed for a kind of a feedback loop, or we will have a detailed insight about the overall parameters which are being considered for a feedback loop. So, as far as in the case of AFM operation with reference to the feedback loop, AFM operation is based on the ability to keep parameters like deflection, amplitude and phase shift constant. This is done by an AFM control system, which is usually a kind of a proportional integral differential system. So, the digital controllers have built-in timers which provides the time base for interruption. It is a code which ensures a well defined and a consistent timing. So, which is represented as DT. A PID feedback loop consists of 3 correction terms which contributes to the Z scanner position at a given time Z of t. So, Z of t, it is represented as P epsilon t plus I dt epsilon I plus d epsilon t minus 1 by dt. So, t equals t to 1 means t minus dt, and epsilon t is the error signal at time t, the difference between the measured value and the set value. So, the as we all know, the proportional is the PID is nothing but the proportional integral and derivative gains respectively. Now, let us go in detail about the overall feedback loop. So, most of the AFM employs P and L only because the differential control leads to instabilities, thus considering a kind of a proportional integral feedback. So, ideally it is represented as Z t minus 1, which is like P epsilon t minus 1 plus I dt to t minus 1 I equals 0 epsilon I. This is considered to be a kind of a PI feedback. The relationship between Zt and Zt minus 1 can be written as Zt equals Zt minus 1 plus P I dt epsilon t plus P epsilon t minus 1. This can be rewritten as Z of t minus 1 plus alpha epsilon t plus beta b epsilon t minus 1. So, A equals P plus I del t and B equals minus P. So, the proper feedback control requires the fine tuning of these PI parameters. as far as these atomic force microscopes are concerned, like with reference to feedback loop, the fine tuning of the PA signal is done by overlapping the forward and the backward scan signals. So, low values of A and B indicate the different profiles for forward and backward scan. Thus, a system response will be very slow. So, will be very slow, and for too high values of A and B, which makes the system unstable. So, the Z piezoelectrics the piezoelectric system, it oscillates at a very high frequency. So, in the commercial system, the optimized values of A and B are derived by an inbuilt algorithm, which takes care of the overall compensation within the arrangement. So, these are some of the key aspects with reference to AFM as a micro and nano robot. Okay, it is a kind of a fundamental where AFM characterization is used. Now, how an AFM is used for a kind of a fiber pulling, let us discuss in detail. So, as far as these fibers are concerned, so we all know, we all are aware about it. So, fibers are widely used for sensing related applications, and then fibers has a potential in such a way that it is also used for kind of a diagnostics. In certain cases, it is used for improving the strength, etc. Now, in this particular case study, we will discuss about this 3D micro and nano fiber pulling, which is a kind of a microfabrication technique in which thin fibers are pulled in controlled manner to achieve a diameter in micrometer or nanometer range to generate a 3-dimensional structures. So, these micro and nano fibers are useful in a kind of a biomedical engineering. It is also used in fiber optics, micro and nano electronics, etc. Some of the commonly used these micro and nano fibers pullings are, one is like AFM tip controlled pulling, another one is called as a flame heated taper drawing, third one is called as a tungsten probe pulling, and the fourth one is called as a polymer drawing. So, in all these cases, so one of the key aspect which we may need to consider is the overall coil diameter and overall length needs to be taken up into consideration. Let us look into the overall methodology, how these pulling capabilities are deployed and how it has an impact on a different fabrication process. Let us see the first concept. So, it is a kind of a AFM tip control pulling process. So, in this AFM tip control pulling process, so we have a AFM tip and then there is a polymer in place. This polymer will interact with the heated substrate, where exactly the material which fiber needs to be pulled is kept, and then a kind of a micro nano fiber pulling is done with an AFM tip when it touches the surface and it tries to pull it. So, as far as in this AFM tip control pulling is concerned, let us consider a kind of a thermoset polymer which is coated on a glass substrate. The substrate is heated to a temperature of close to around 90 degrees Celsius. Now, which is mainly meant for curing the polymer. Now, we have a silicon AFM tip which is used to pull the fiber in a vertical direction as shown over here. So, what happens is, this is a kind of a tip which is being inserted into the cured polymer, and there is going to be a certain amount of curing which exhibits. This results in a nanofiber formation between the substrate and the tip. After a certain waiting time, the nanofiber itself cure at a room temperature due to its high aspects, and in the case of application perspective point of view, so it is highly used for kind of electronic circuit, sensor, as well as a kind of a robotic mechanism. So, this is a kind of concept where AFM is used. So, some of the key parameters which is taken into consideration are the overall diameter of the fiber, length of the fiber, and the density per unit area of the fiber. Which will heavily contribute towards the kind of a manipulation which exhibits over here. Now, let us discuss about the next concept which is called as a flame heated taper drawing. So, as far as in this flame heated taper drawing is concerned, if we try to look into this particular process, so there are two standard, this is a kind of a standard fiber which is of a particular diameter. So, in order to like treat it, so ideally there is a flame which is being introduced into it. So, with reference to the flame, the complete material gets heated up and then you can pull the fiber. So, the fiber is pulled with a kind of a pulling force which is exerted over here. So, there is a kind of a feedback system which exhibits where there is an input signal in place and then the overall change in the input signal is measured from the output signal system. So, what is happening is when the flame heats this fiber, the fiber is pulled up or the fiber is deformed and finally, we get a thin structure coming out of it. So, here in this particular case, a hydrogen flame is used for heating the optical fiber. A constant pulling force is applied to the fiber during the heating to reduce the diameter to a desired value. As far as optical signal is concerned, so the optical signal is passed through the fiber during the pulling process. This is ideally done for a kind of an in situ monitoring of waveguiding properties such as propagation loss, multimode interference and a group velocity delay. So, these kind of system are mostly used to draw silica with this kind of pulling process for a standard optical fiber. And one of the key aspects, since a heat is involved in this, the flame heat can lead to a kind of a turbulence and it can also result to a kind of a contamination in the nanofiber. So, in order to avoid that, so ideally what it is done is, so they are kind of, it is wrapped with an insulating medium, so that appropriately the contamination can be eliminated. This is one way, or the other way is something like it is completely done in a controlled environment, so that the contaminations can also be controlled. So, this kind of contamination can also be eliminated by using an electric heater or a laser heating in a sapphire tube while pulling. Okay. Now, let us discuss about the next configuration, which is a kind of a tungsten probe pulling. This, as far as this tungsten probe pulling is concerned, it's a kind of a quite a kind of a manipulation process which in which a solution phase of the material is taken up into consideration. From the solution this you try to go for a wetting of a particular tip and then when we try to manipulate it, we get a kind of a thin nanofiber coming out of it. So, it is something like this, like we might have observed, like when we have a tip of pencil, when it is made to dip on a particular liquid region and when we try to pull it back, we see a thin film of layer which comes out of it in the form of a thread. So, this is a kind of concept which exhibits in such a way that you have a probe and through the probe you are trying to get it. Okay. So, as far as in this tungsten probe pulling is concerned, it is mainly meant for polymer or biological sample is put on a glass slide in a kind of a bulk solution as shown over here. So, the glass slide is heated to reduce the viscosity of the polymer solution. So, this tip of the tungsten probe is approached in the solution at one end and the probe is retracted in this direction along the surface of a glass slide at a constant speed to produce a nanofiber. So, if you closely observe in the schematic, so we have a glass slide and then there is a provision for heating the sample, heating the slide to have a control over the viscosity. In addition to this, this should be done in a kind of a controlled environment and one of the most important aspect is like it is expected that there is no air flow within this particular domain. So, in case if there is a airflow is there, appropriately there is a chance that this nanofiber may break and we won't have any kind of like there will be a kind of a lattice deformation which exhibits on this nanofiber. So, this is a kind of a simple manipulation technique where a tungsten probe is used to pull the fiber based on its adhesion characteristics and based on its wetting property. So, here one of the key point which we may need to look into it is the tip plays a vital role. The overall surface characteristics of the tip plays a vital role in wetting the particular liquid and then pulling the particular liquid in an appropriate directions. Now, let us discuss about this polymer wire drawing process. So, as far as in this polymer wire drawing process, almost the mechanism perspective point of view, almost this tungsten probe pulling and this polymer drawing is almost the same. However, in the case of a polymer drawing, so it is a kind of a wire drawing process which is deployed. So, like in this particular case, so if we closely observe the overall construction of the system, so we have a iron silica rod in place, then there is a hot plate with a molten polymer which is placed over here. This iron silica is made to dip on the molten polymer and then it is kept on a static phase. So, this polymer such as poly-trimethyl terephthalate PTT is put on a heating plate. It is heated and maintained at 250 degree Celsius during the drawing process. Iron and a silica rod is approached and its tip is immersed in the molten PTT layer. Then the rod is retracted in a vertical direction at a constant speed of in the order of 0.1 to 1 meter per second, producing a PTT nanowire between the molten PTT and the tip of the rod. So, as far as in this particular case is concerned, the diameter of the wire and the overall length of the density of the wire depends upon the rod retraction in the vertical direction. Okay. So, this is a concept which is being successfully established, especially for drawing wires in the especially which is involved in a kind of a polymer drawing which are being established. Now, as far as these application perspective point of view, like it is these kind of optical fibers are highly used for kind of like gas absorption spectroscopy. So, like if you see the overall construction of it, let us consider a crucible which is filled with molecule and then which is a kind of a gas and then which is the gas needs to be investigated. Okay. Now, we have a kind of a fiber in place where there is going to be an input signal and an output signal and then the numerical aperture of this is close to around 125 micrometer and then in between we have a kind of a 500 nanometer which is pulled because of either of by using either of these either of this process. The optical input is passed through a double tapered optical fiber. So, the diameter of the waste section is usually close to or less than the wavelength of the light. So, the waste section is exposed to the species under observation. The molecules of the species are absorbed on the fiber substrate surface and absorb the fraction of the optical signal. So, absorption of light by molecule lead to attenuation of signal received at the output. So, ideally the strength of the gas absorption lines can be used to find the gas concentration, that is I equals I naught exp minus alpha LC. So, I is the output intensity, I naught is the input intensity, alpha is the optical absorption coefficient, L is the length of the fiber, C is the concentration of the gas. So, ideally this acts as a kind of a generalized equation to investigate the overall gas concentration in the system. Now, such kind of fibers are also used for other kind of sensing elements. So, one of the sensing elements includes this Mach-Zehnder interferometer. So, as far as in this Mach-Zehnder interferometer is concerned, it utilizes a kind of a evanescent waves for sensing, and this evanescent wave is a small portion of light that comes out of the optical fiber during a total internal reflection. So, when we try to observe this Mach-Zehnder, so we have two sets of wires which are being placed and these are being couplers and there is a kind of a sensitive arm which is available. So, in the case of a nanowire arm, the sensing arm with a certain length of a sensing area and nanowire 2 refer arm refers to the reference which is used to kept isolated for measurement. So, this act as a kind of a standard system and this acts as a kind of a sensing system. So, this acts as a standard system and this acts as a sensing system. So, from the standard system we can see like we keep that as a calibration part, and from this calibration part we can sense how much is the deviation which exhibits over here, and using a sensitive area we can understand like how sensitive is this system being deployed. Okay. So, for these applications these kind of MNF pulled fibers can be efficiently used. Now, let us take an application where a fiber brag grating is deployed. So, this is a process in which using a fiber pulling the fiber brag gratings are inscribed on the fiber pulled samples. So, this fiber brag grating is considered to be one of the successful fiber based structures for optical sensing. It has high compactness and strong near field interaction with the surrounding medium, and it has a high resistance to mechanical and thermal shock, and it has a high sensitivity and small footprint with larger dynamic range and faster response. So, to fabricate such kind of MNF grating with much smaller fiber diameter and shorter overall length, a femtosecond laser pulse irradiation is used. So, ideally with a wavelength of 193 nanometer ARF XML laser, which is used for inscription, and sometimes in certain cases focus ion beam milling is also used. So, this laser beam is irradiated with this MNF grating at different points with increasing the refractive index of the core locally. So, this how like these gratings are being are deployed. However, on an application perspective point of view, these gratings are efficiently used for a kind of a condition monitoring or for kind of a vibration analysis. In certain cases, it is also used for a delicate, it acts as a highly sensitive system which is used for a delicate measurements. How these fiber pulled samples are used for resonators. So, when a kind of such kind of samples are concerned, so we have a loop in place with an optical fiber, and these are some kind of MNF assembled samples. So, we have different configurations which are being deployed. One is a kind of a loop based system, another one is called as a knot based system, and we also have a stack of coil based system. So, where in the case of a resonator, when an MNF is assembled into a closed loop, a ring resonator can be formed by an evanescent coupling at the overlapping area. So, the typical geometries are loosely assembled loop, or either it is a tied knot or a stacked multi-coil kind of resonators, and MNF loop resonators is a type of a Sagnac interferometer, where the coupling between the adjacent MNF segments leads to almost a complete transfer of light from one segment to another. As a result, the electromagnetic wave makes several turns in the MNF loop, forming a resonance in the MLR transmission spectrum. So, highly as far as these particular systems are concerned, these particular systems are effectively useful for temperature measurement, humidity measurement, magnetic field as well as electric field sensing. So, these are some of the key parameters which can be measured using such kind of resonators. Now, let us discuss about this MNF coupler. So, as far as this MNF coupler are concerned, so like let us consider we have the input P1, and then there is a waste region where exactly a transition region exists, and then there is going to be a reflective ring. So, through this a light is passing through it, and it passes through the waste region, and through the reflective region it comes out of it. So, this is a kind of a coupler, or this is a kind of a transition region which works on this particular region, and MNF is bent and the two free ends are twisted together to form a Sagnac loop. So, the twisted region is laterally fused and tapered, which will act as a kind of a coupling region. It comprises of 4 ports, true transition region, one central base region, and a reflective ring formed by linking port P3 and P4. So, the input light enters the waste region through the port P1 and the coupling process proceeds along with the coupling region. At the end of the coupling, the light continues to propagate within the Sagnac loop and finally enters the waste region again, but in an opposite direction. So, this is how the system works. Now, in the case of the second coupling, that is when the second coupling happens, hence the Sagnac loop in the proposed structure can be considered as a kind of a reflector. The corresponding output light at port P2 is monitored and analyzed by an optical spectrum analyzer. So, these MNF coupler is a kind of a useful structure for highly sensitive optical sensing, biosensing and feedback systems in laser, and these MNF couplers have been widely employed for detection of microforce, magnetic field, current, seawater salinity, temperature and humidity. So, these are the different parameters which can be measured using this particular system. So, other applications and then other important characteristics which we will be discussing it in the upcoming classes.